are continuing. It's my pleasure to introduce Peng from USC, who I have not yet met personally, but I hear great things about clearing matching markets efficiently. Well, you don't have to read this. You have 45 minutes. I'll give you a 10, 5, 1, 0, or 5, 1, 0.
Yeah. Thanks so much, Steve. Again, my name is Peng, and I'm assistant professor at the University of Southern California. I'm very excited today to attend this workshop to share about my research and also to learn from all of you. And the paper I'm presenting today is joint work with Itai Ashlaki, Mark Braverman, and Yash Kanoria. So let me begin by parsing the title. The question we're thinking about is how to help a two-sided matching market reach a good outcome, despite the fact that learning about one's own preferences and communicating that to the market is costly. So for example, my home department in data science and operations is hiring 2 open-rank tenure-track faculty this year. And it is very costly for an applicant to fill out this long application and get their reference letters. It also takes us a lot of time to read through all the applications, and we only have a few slots for on-campus interviews. So it's quite likely that because of the limited capacity to learn our preferences and communicate that to the market, we might not be able to get matched to the most suitable candidate who is also willing to come. And so at a high level, this paper is trying to make markets such as the academic job market clear more quickly. And the 2 prescriptions we give to help this problem are informative signaling and match recommendations. Informative signaling is about designing the message space of what agents can communicate. And match recommendations is about encouraging certain agents to reach out to certain others or discouraging certain interactions. So here is the outline of my talk. I'll first talk more about the motivation, the paper's contribution, and relationship to related work. And then I'll talk about 2 sets of results in 2 sets of theoretical models that are related. So first, again, the broader research agenda we're trying to address is to facilitate matchmaking in two-sided markets. And the problem that we are dealing with, called congestion, is when the market cannot process or communicate information quickly enough to reach a good outcome. And this has empirically been demonstrated to be a serious problem in many markets. And addressing this can help improve the welfare of the participants and also help the platform be competitive. So to address this research agenda, there's a series of steps. So we need to document what are the current inefficiencies, a theoretical understanding of what is possible. And based on the above, try to come up with implementable prescriptions and hopefully test them in field experiments. So this is a long research agenda, and today we're only focused on this theoretical part. So the model that I will present has some distance from actual markets like the academic job market. But at the end of the talk, I'll talk about some qualitative insights that are closer to real markets. So how do we define market efficiency? So in this paper, our definition is a no congestion outcome using the minimum amount of communication and information overhead. And here, a no congestion outcome is a stable matching, which is the market equilibrium when everyone knows their entire preferences and can communicate as much as they want. So let me just review what a stable matching is. So suppose we have 2 candidates going for 2 academic positions. And Alice is suitable for both UCLA and USC, but she prefers USC clearly. And Bob is only suitable for the USC position. And USC prefers Alice over Bob. Then in this simple market, the only stable matching is the blue one that matches Alice to USC and leaves UCLA and Bob unmatched. The reason is, under any other matching, Alice and USC would like to deviate because they prefer each other over the other people. in a small example like this, it's easy to find a stable matching. But you can imagine when the market is large, it may be hard for Alice to know that USC is her favorite school out of all the places she can get into. And equally, it may be hard for USC to determine that Alice is the best candidate given all the people who will actually want to come. Because whether Alice can get into another school or whether another candidate will come to USC depends on their options. And they may be waiting to hear back from other candidates and other schools. So it's possibly hard to find a stable matching. This may be too hard to ask for. In fact, there is this previous impossibility result, first due to Ilya Siegel and later improved by Gonchowski et al., which is as follows. So there exists a distribution of preferences, so some two-sided matching markets, in which any way of finding a stable matching with high probability requires a lot of communication. So here, N is the number of agents in this market. And just to give a background, for everyone to communicate their entire preference ranking over the entire market requires n log n bits. So asymptotically speaking, this is just log n from communicating your entire preferences. So one way of interpreting this result is that congestion is a problem to stay. There's nothing you can do about it in a large matching market. There's no way to find a stable matching in such markets. However, when we read the proof of this result, you find that it requires these pathologically correlated preferences in which if I like someone, most likely they will not like me. So it's anti-correlated preferences. And that makes it so that it's very hard just to identify whether two people mutually like each other. And the contribution in this paper that I'm presenting to you is that when we have more natural restrictions on preferences, which I will describe, make precise in a few slides, it is possible indeed to find a stable matching with high probability without too much communication. Agents don't need to learn their entire preference ranking, and also people have good incentives to follow the policy. And although this is a theoretical result, we can learn from the protocol that we produce some insights about what kind of signals are helpful. So there's market design that can be motivated from this. And now let me talk a little bit about the related work. So Roth and Xing is an early paper that documents this problem of congestion in matching markets. And they show how in many centralized labor markets, because of congestion, people act earlier and earlier and earlier, and the market unravels. One solution to this is to come up with a centralized matching mechanisms, like what they do for the medical residency match. However, even there, that doesn't solve the problem because the market is still congested in the sense of you need to actually interview at the place you want to work at, and interviews are limited. So congestion can still be a problem even in centralized matching markets running a stable mechanism. More recently, Andre Fratkin found that in Airbnb, at a certain point in time, many requests get turned down simply because the room is unavailable. And once Airbnb started better tracking availability information, that simple intervention improved the welfare of the system in terms of the match rates significantly. And John Horton also found similarly that in Upwork, if you allow people to signal their capacity, that can help improve market efficiency. But the empirical literature left out the question, besides these simple interventions that we can think of, how much more room is there to make the market more efficient? In terms of theoretical papers, previous papers in signaling in matching markets, as well as search and matching, all assumed some kind of a signaling mechanism or a way in which, a game in which people participate and matches are formed. And in contrast to that, our approach in this paper is coming from this computational communication complexity literature in computer science, in which the bounds that we produce are based on information theory, so not dependent on any particular signaling mechanism or any particular way of match formation. And there's also other models in which people learn about their preferences differently. One of close related papers by Nicole and Irene and Jacob and Brandon. And I'll talk in 2 slides about our model of preference learning. And finally, our paper builds on the literature on communication complexity in computer science, as well as the models of large two-sided matching markets. So now I'm going to talk about the first model, which I call separable markets. So we need some kind of restrictions on the market in order to avoid the impossibility results. But hopefully, I'll show the assumptions are mild, and then we can see that the previous linear lower bound on communication vastly reduces, and we can come up with an efficient way of forming stable matchings, which I call communication efficient deferred acceptance. So now this is the model in 1 slide. So I'm going to go through this slide fairly slowly. And so what we mean by separable markets is there's a one-to-one matching markets with non-transferable utility with workers and firms. For workers, we don't have any assumptions on their preferences. They can be arbitrary. And for the firms, their utilities are additively separable into 2 terms, a public score and a private score. That's why we call separable market for this additive separability on one side of the market. The public scores corresponds to the observable characteristics of worker I and firm J. And the private score corresponds to the unobserved idiosyncratic components. Notice how the public scores can depend on the IJ pair. So this is a very flexible model that embeds almost all discrete choice models used by empirical researchers. And one assumption to make this model not embed general preferences is that this epsilon term, the private scores, are sufficiently important relative to the public scores. And mathematically speaking, we assume that the private scores, the tail is at least as heavy as an exponential distribution. So the hazard rate is at most 1. And also the range of the public scores is bounded by some polylogarithmic function of the market size. That's to force this term to be sufficiently large relative to this term. And now, notice that no one actually knows the workers don't know their own preferences, and firms don't know their private scores up front. But every agent needs to learn about their own preferences by using this choice function query, which means given a set, is there any person among this set that I prefer over being unmatched? And if so, who is my favorite one? So this is perhaps the weakest point of our model, because one could argue that finding my best partner out of a set of 1,000 candidates should not just take one choice function query. However, this is needed for the analysis, and also it may be more justifiable in these digital platforms in which you can easily search over using some criteria and find the best partner out of a certain set using filters and rankings. But given this is our assumption on how people learn their preferences, matchings happen based on this communication protocol, which is this precise way to formalize communication. You can think of this as there's a whiteboard that people can post on. People can only communicate using the whiteboard, and everyone agree what will happen based on the history of what is written on the whiteboard, who should write next, and what should they write, and what does that mean? So that's a communication protocol. And a matching protocol is a communication protocol that produces stable matching with high probability, meaning that as the market size goes large, we can make this probability that we find a stable matching to converge to 1. And how we measure communication is based on the amount of bits of information we write on this whiteboard. And preference learning cost is how many choice function queries agents need to make to be able to participate. Ramesh, you had a question?
Yeah, I had a couple of questions. So one is, I guess this choice function can take sets of any size as well?
Yes.
Okay. And then does the size of the set figure into the communication cost when you're measuring them?
Yes, so, okay, that's a good question. So you can think of this as two models embedded in one another. So one model is the communication model, this whiteboard. And so when people normally talk about communication complexity, they assume people have infinite computational power, and they can, we only need to bound the amount of communication that goes on, but we don't really care about how people figure out what to communicate. And so we build on top of that that standard model, this additional thing that in order to play this communication game, you can only learn about your preferences using oracles of this size. So to answer your question specifically, yes, these two are separate. So I can do all the preference learning I want, and that counts only towards the preference learning cost. But whatever information I communicate as a result of what I learned about myself, that gets calculated in the communication cost. So these are sort of orthogonal ways of counting cost. However, in order to come up with useful communication, you probably have to do some preference learning. Otherwise, you're just communicating random things. Does that make sense? Yes. Nicole?
So when you get an answer to one of these queries, you learn stuff about other elements like of that set, right?
Yes. So when you get the answer to the query, you learn about so your preferences. You learn that this UJI is the so for firms, you learn that UJI is the highest among all the other I's in this set, and for workers, you know that you know that firm is your favorite one. So you do learn a little bit about the other things. That's correct.
You learn that value of UJI, not just...
You don't learn the value. You only know that is the maximum among all the other things. But you do know the AJIs. But you never observe the actual value. You only know it's the max. Any other question?
You assume strategy proofness. I mean, everything is revealed.
Yes, so that's a good question. This question is about incentives. So for the majority of the talk, let's assume everyone follows my protocol. So people are acting as I desire. And then I'm going to prove that they don't have any incentive to deviate from that. But for now, let's assume that they follow. Any other question? Yes. Okay, so that was a little abstract. Let's consider an example of a matching protocol. This is the Gale-Shapley deferred acceptance algorithm, the worker proposing version. So this is the most standard algorithm for finding a stable matching. And then we'll see that this algorithm has a high cost as measured by the metrics I just defined. So as a review, how this algorithm works is we pick an unmatched worker, and that worker applies to their favorite firm that they have not applied to. And this they can figure out using one choice function query. And then that firm compares this applicant to possibly being unmatched, or if the firm is previously accepted another worker. And then the firm will pick the best out of these, keeps the one the firm likes, rejects the other, and then the algorithm terminates when every worker is either matched or has been rejected from all the places they prefer over being unmatched. And using this algorithm, based on the result by Itai Shlaki, Yash Knoya, and Jacob Leshno, if you consider this example of a separable market in which preferences are just IID, and there's just one more worker than firm, then their analysis implies that this algorithm does poorly in terms of communication and preference learning. So there's linear amount of communication and almost linear amount of preference learning. And this is the same as the impossibility result previously. And the intuition here is the excessive competition when you have one extra worker makes it so that there's a lot of rejections. And the thing to do in this market is actually to let the firms propose rather than the workers propose. So now the question is there a market, a separable market in which no algorithm can do very well? And here is an example. Let's just take a random market with n workers and n firms, everything IID. The catch is that it's a sparse market, which means that each agent will only like someone else with probability 1 over square root of n. So that means if we pick an arbitrary pair of firm and workers, the chance that they will mutually find each other acceptable is 1 over n. And that means that this market, it will be very sparse in terms of the mutually acceptable pairs. And so the intuition is trying to find these mutually acceptable pairs. It's like finding needles in a haystack. It's very hard. And standard arguments used based on communication complexity, based on this disjointness, reduction to the disjointness problem, can show that square root n communication is necessary in this problem. And so we cannot do better than square root n for separable markets. The question is, can we achieve this lower bound? And the main result of this paper is that we can. And I'm going to describe the algorithm that does it next. Yes. So let me talk about the main idea. So in the end, we want to discourage people who shouldn't apply from applying. And so we want to discourage workers who have a low utility, who wouldn't have gotten in anyway if they applied. Why waste your own time and waste the firm's time from applying? And so if someone has a low utility, the firm has a low utility for this person, that means that both the public score and the private score has to be low. So the main idea is this. If firms can solicit workers who have high private score and tell them to come apply, then the firm can set a threshold on the public scores saying, unless I solicited an application from you, you need at least a certain qualification requirement on your public score in order to qualify. Yes, so the reason is the first one will get the people with the high epsilons, and the second one will get the people with high A's. And if you neither have high epsilon or high A's, that means you shouldn't apply. That's the basic idea. Any question here?
So
yes, Steve?
Is the firm setting the AJI, the ZJ, before or after knowing the realization of epsilon JIs?
Yes, this is a good question. I'm going to address this in the next slide. So this is the zooming out, the large idea, but the details of the protocol is here. This is the communication efficient deferred acceptance. So these qualification requirements are done in an adaptive fashion. So first, we set them to be very low. Everyone can apply. This means the lowest possible public score. And in the first step, all firms signal people they like idiosyncratically. They have a high private score for. However, since firms don't observe the private scores, so one way to accomplish that using choice function queries is we can bucket workers based on their public scores. And out of these are like the people who look bad on paper. These are the people who look maybe somewhat better on paper. These are the people who look best on paper. And from each bin, we select the top 3 square root n, so a certain number of my favorite workers in this bin. And that will pick out from each bin the people who have the highest private scores. Because out of people who look the same on paper, the people I like are the ones with the good private scores. And after firms all send these signals, now we run the worker proposing deferred acceptance with one change, which is that workers are only to apply if they either receive the signal in first round or they have a high enough public score. And if these requirements never change, then this is basically the worker proposing deferred acceptance. And what makes this communication efficient is that firms update their qualification requirements every time they receive a sufficient high number of newly qualified applicants. So the idea is, if I see a lot of applications from people who look good on paper, because the private scores are IID, one of these applications are probably pretty good. So after this number of applications with high probability, I can increase my bar. Yes, and the reason why this protocol works is that we can prove it replicates the original worker proposing deferred acceptance with high probability. And basically, these ZJs doesn't increase with high probability. No one who would have gotten accepted would have been disallowed from applying. Yes. Any questions on this one? Yes.
The top 3 square root n workers, that's by the public scores or by the actual UJI?
Again, yes. So this is by the choice function query. So I'm going to find my top one, and then I will find my top one among the rest, etc. Yes, everything here can be done using knowledge only of the public scores and the choice function queries. Any other question? Yes, Jacob?
If we could have just observed the private scores
Yes.
as well, would this be the same or simpler?
Oh, yes. If you could observe the private scores, you could make this first part. You can make this first part simpler, and then yes. But this part, you still need some way to increase these. So this is sufficiently simple. You might be able to reduce these constants and log factors, but so observing the epsilons will help simplify step 1, but not step 2 that I know of.
It's just a constant. It just helps with the constants, not.
Yes. Possibly some log factor. Yes. Any other question? Yes. So the properties of this protocol is that it yields a stable matching with high probability, and it achieves the lower bound, the square root n, except I'm hiding polylogarithmic factors of n inside this star. And also, back to the question over here about incentives. So deferred acceptance is not incentive compatible for anyone to begin with. But we can show that this communication efficient version of DA is with high probability as incentive compatible as DA, in the sense that whatever incentive properties we had with deferred acceptance, we have it here. And so in particular, it means that if the market is such that there's a unique stable matching, which has been demonstrated empirically to be approximately true, and there's theoretical papers that motivate it, then it will be an epsilon equilibrium for everyone to follow this. Yes. So that's and the 3 insights we get from here are as follows. So first, we want to help agents estimate their chance of getting someone. So that's done with this qualification requirements that's updating and using the public scores. Second, we want both sides of the market to signal interest. That's done by firms applying, workers applying, and firms also doing the preference scores. It's crucial to have both sides being able to initiate. And finally, we want to discourage or prevent these hopeless applications, which is done by only allowing workers who either were solicited or looks really good on paper to apply, but not people who are unsolicited and look bad on paper. Yes, Ramesh?
Maybe not be a fair question, but Yash, since you gave your talk yesterday, I'm kind of curious, like if you look at number 2 and you contrast that with what you were talking about yesterday.
Yes.
If the market is unbalanced, do you feel differently about number 2? I mean, your conclusion yesterday essentially is that you there are regimes in which it's best for only one side of the market.
So that's a very good question. I will actually talk about this question in about 3 or 4 slides.
Oh, perfect.
Great. Yes. So this is concludes the first part with the separable markets. There's some disadvantages to SIDA, which I will talk about now, and motivates another model with another simpler model with a simpler protocol that addresses Ramesh's question of what happens, whether we should allow 2 sides to signal. Yes. So the limitation with SIDA is that applications are sequential, and also firms need to be broadcasting, need to be publicly proclaiming their ZIJs their qualification requirement to everyone. And that could be a problem because a worker doesn't know whether to apply before knowing the qualification requirements. And the qualification requirements depends on other workers' applications. So there's still some congestion that's going on because of this sequential nature of this mechanism. So it's desirable to come up with what is called a 2-round protocol, in which everyone does all their signaling simultaneously, and based on 1 round of signals, make up their mind on whom they like and send it to, say, a third party to run a stable matching mechanism. So you can think about this as the medical match. Everyone interviews or sends signals, and then based on that, people participate in the medical match with a short ranking of whom they prefer. So that's the 2-round protocol. However, it's impossible to find the 2-round protocol for all separable markets, and here's an example why. So there's horizontal heterogeneity. So 2 types of workers, 2 types of firms. Think of these as there's N+1 PhD students who want to be a research faculty, and N of them who want to just teach college classes. However, there's few number of research-oriented positions and more teaching positions. And in any stable matching, there will be one unlucky research candidate who has to match with one of these unfilled teaching positions. And a priori, it's really unclear which of these edges it's going to be, because the identity of this unlucky person really depends on the preferences of these positions. And the identity of this position depends on the preferences of these candidates. And so in a 2-round protocol, in order to reach a stable matching with high probability, everyone here needs to signal everyone here, and that's too much. And so horizontal heterogeneity makes this impossible. So in practice, this motivates having maybe an aftermarket after the main market in which these match. So an open question is how many rounds do you need in general? But staying with 2 rounds, we can only hope for some positive results if we allow some more structure, for example, vertical heterogeneity. So in this, what we call tiered random markets, this second model that I'm talking about. So agents are partitioned into tiers that everyone knows about. So these are the top, the star PhD candidates. These are the next tier who have maybe fewer publications. These are the people who don't have publications. And here are the tier 1 schools, tier 2 schools, etc. We assume that people always prefer the better tiers, but within each tier, it's completely random how they prefer. And also, everyone finds everyone else acceptable. That's the assumption. It's also called a block correlated preferences in previous papers. So the question here, back to Ramesh's question, is who should signal who? Who should initiate contact? And so in next 3 slides, I'm going to give 3 examples to illustrate what's going on here. In the first example, let's assume there's 1 tier of each. So this is just an unbalanced IID market, and there's fewer firms than workers. And the result that goes back to Patel is that if you allow firms to do the firm proposing deferred acceptance algorithm, with high probability, every firm will be matched to one of their top log square n candidates. This implies that in this market, let's just let the firms propose, and then they just signal, every firm signal their top log square n candidates. And with high probability, the subgraph induced by these contacts will contain a stable matching. Yes. So now let's complicate this picture a little bit. Let's assume there's 2 tiers of workers. So this goes back a little bit to Ramesh's question, because if we look at the top workers, they are in a better position than the firms, because if we forget them, they are on the short side. However, if you look at the firms that are left over after the top workers have picked, they are in a better position than the bottom workers. So here what you want to do is to have the top workers apply to a signal, and then have the firms signal to the bottom workers. And you can show that this is an efficient 2-round protocol. And as a third example, let's consider workers are IID in the sense they're homogeneous ex ante, and firms are vertically ranked, meaning that each tier just contains 1 firm. So in this simple example, the unique stable matching is induced by serial dictatorship by the firms. The first firm picks, the second firm picks the best remaining. But since there's IID preferences for workers, most likely the second firm is not going to collide with the first firm. So in fact, you can show an efficient 2-round protocol is in which the jth firm, the jth ranked firm, apply signals workers, and then this ratio, n over n minus j plus 1, that's the inverse of the proportion of workers who are not matched to better ranked firms. So basically they get to pick their favorite person except if it collided with someone above them. And if they send this many signals, that cover the case in which they collide. And you can show that these sum up to, on average, it's going to be log squared n, number of signals. And so in the general case, for general tiered random markets, the protocol works as follows. It's the aggregation of the ideas previously, but the proof is more complicated. Essentially, each agent will signal people in what is called the target tier. What is the target tier? These are the people on the other side who are just slightly in a worse position than I am. So the endpoint, the bottom here, is slightly lower. So the target here of these people are the firms here. The target here of these firms are the workers here. Everyone just signals slightly below them. And the amount they signal has its log square n divided by this rho n. And this rho I is similar to the example with the serial dictatorship. This is to prevent, this is the proportion of partners that are not taken by better ranked people. So combining all these ideas, we get this protocol which has the good properties as the CETA protocol. The bounds get much better in this market. And also, it's a 2-round protocol in which everyone does their signaling at the same time, and all communication are between pairs of agents rather than broadcasting to the whole market. The insights are the same as before. Basically, we help agents estimate their chances using this tier structure. We allow both sides of the market to signal. And we only allow people to signal down, but not go up. So now, with the last few minutes, I'm going to talk about practically how would one implement this. What does it mean? So how to help agents estimate their chances. So for cases like university admission, in which there's a threshold cutoff on the score of an applicant, people can publish forecasts of these, which is done in universities, I believe, in Israel, Iran, and other countries. Also, for digital platforms, you can imagine these Upwork or other platforms using their data to create some kind of a prediction tool of whether a prospective partner will reciprocate interest. What's my chance of getting someone? And this tool can get better if we collect better data. So for example, Ramesh and Zhang Horton, they work with Upwork in which to allow firms to signal the quality. Am I looking for high quality workers and willing to pay more, or I'm just willing to get someone to get the job done? So making the preferences of firms more expressive allows agents to better predict, okay, now I see this employer is hiring, they want quality people, okay, am I a good match or not? So making things more expressive helps the market to sort more efficiently. And we can also maybe use the idea in CETA in which we look at how many applications a firm already is getting in real time. And if a firm is getting a lot of good applicants, we can say this is a hot firm, like what happens on Zillow with a hot property. And then maybe use this to improve the prediction tool. These are ideas about number one. So number two, how do we actually allow both sides of the market to signal? So for the academic job market, it would be helpful if there's some comprehensible and searchable registry of all potential candidates this year. So for example, in the operations market, there are some attempts to make this independent website in which everyone tries to register. That's an ongoing effort. And in the economics job market, departments keep their list of their top people. So in some sense, in the economics market, schools can potentially initiate contact as well without the person actually applying. And this will help my department, for example. We're trying to recruit 2 positions. That's very hard, especially if it's open rank positions. So having some way we can target recruitment will be helpful. But for large online platforms like employment platform, it's hard for firms to signal individual workers because there's too many of them. So you can't really, the only way to help firms to initiate contact is if we collect good information on the workers and design some way for firms to say, I'm going to want to signal all workers who have this amount of experience, who have done X and X and Y, to say apply. And it's important to make sure that the number of people who match the filters is sufficiently small so that these signals are informative. But this is a way in which, without knowing identity of individual workers, firms can signal to specific people. And finally, how to prevent hopeless applications. I already talked about how we can track availabilities of the other people, but we can also restrict who will contact whom. So this goes back to Yash's paper he talked about yesterday. For example, in the dating app, Bumble, the women are the ones who have to initiate contact. And typically, women on dating apps are on the short side of the market. So it makes sense for them to initiate rather than the other way. So it's not that we always want both sides to be initiating contact because, again, in the 3 examples I give, in the first example, we only want the short side to initiate and restrict the other side. So match recommendation is both about recommending and also preventing certain contacts from forming, which are bad equilibria. And finally, we want to, when we're doing a search tool to rank people, we shouldn't be training the algorithm to only rank people based on my own preferences, but also based on whether that person will actually reciprocate. So yes, and that will be more useful for helping the market converge. And so that concludes my talk, and I'm happy to talk more offline. Thank you.
Sid, you want to take it away?
Okay, I'll help you.